Deep in the far reaches of our solar system, where sunlight is little more than a faint glimmer and temperatures plunge hundreds of degrees below freezing, something extraordinary defies all expectations. Picture a landscape so cold it should be frozen in time, yet here, towering ice volcanoes erupt violently, sending plumes of slushy water, ammonia, and methane soaring into the void. These aren't the fiery mountains of Earth, but Crivell, Conos' alien geological marvels that rewrite the rules of planetary activity. And the most astonishing part, at least 29 of them are still active today, hidden on distant dwarf planets, whispering secrets about the forces that shape our cosmic neighborhood. What could possibly fuel these eruptions in such extreme cold? How do these frozen worlds, so far from the sun's warmth, maintain enough energy to keep their icy volcanoes churning? The answers challenge everything we thought we knew about geology, heat, and even the potential for life in the darkest corners of space. Each eruption is a cosmic puzzle, a clue buried in ice that could reveal how dwarf planets evolve, what hides beneath their surfaces, and whether these mysterious bodies are more dynamic and more alive than we ever imagined. This is the story of those 29 ice volcanoes, a tale of curiosity, cutting-edge science, and the relentless quest to understand the unknown. We'll journey to the edges of the Kuiper Belt, where dwarf planets like Pluto and Ceres defy their quiet reputations with bursts of geological activity. We'll explore how spacecraft like New Horizons captured stunning evidence of these eruptions, turning textbook assumptions upside down. And by the end, you'll see these frozen worlds not as static relics of the solar system's past, but as vibrant, evolving mysteries, ones that might just hold the key to unlocking the story of our cosmic home. So buckle up, the universe is about to get a lot more fascinating. To understand these alien eruptions, we need to rethink what volcanoes even are. On Earth, they're mountains spewing molten rock, fueled by our planet's fiery core. But cryovolcanoes operate by entirely different rules. Their power comes from cold chemistry. Instead of scorching lava, imagine a slushy mix of water, ammonia, or methane bursting through an icy crust, freezing almost instantly in the vacuum of space. This isn't science fiction, it's happening right now on dwarf planets like Pluto, where towering cryovolcanoes like Wright Mons stretch over 3 miles high, dwarfing even Earth's largest volcanoes. What keeps these icy giants erupting? The secret lies in the hidden heat sources buried beneath their frozen surfaces. Unlike Earth, where volcanic activity is driven by a molten core, these distant worlds generate heat through surprising mechanisms. Tidal forces, the gravitational tug of war between moons and their parent planets, can flex and warm the interior of icy bodies, creating pockets of liquid beneath miles of ice. Radioactive decay plays a role too, as elements like potassium and uranium release energy over billions of years, slowly melting subsurface reservoirs. Even the peculiar antifreeze properties of ammonia mixed with water can lower the melting point of ice, allowing slushy eruptions in temperatures that would freeze Earth's volcanoes solid. The landscapes these eruptions create are unlike anything on our planet. On Ceres, the dwarf planet in our asteroid belt, cryovolcanic domes like Ahuna Mons rise like lonely sentinels, their smooth slopes built by countless slow-motion eruptions of salty mud. Pluto's frozen plains, meanwhile, bear wrinkled flows of nitrogen ice that oozed like glacier toothpaste across the surface. These aren't dead worlds, they're dynamic, evolving places where geology plays out in ultra-slow motion, reshaping terrains over millions of years. But the biggest question isn't just how these eruptions happen, it's why they persist. Dwarf planets are tiny compared to Earth, with far less internal heat to spare. Yet somehow, they've kept their cryovolcanoes active long after scientists predicted they should have frozen shut. The answer might rewrite our understanding of how small celestial bodies age, and whether some could even harbor hidden oceans beneath their icy shells, kept liquid by the same forces that power their eruptions. This isn't just geology, it's a cosmic detective story. Every plume spotted by spacecraft like New Horizons or Dawn is a clue, hinting at the complex interplay of chemistry, heat, and time in the solar system's farthest reaches. And as we'll see next, these icy eruptions might do more than reshape landscapes. They could hold the key to something even more extraordinary, the potential for life where we least expect it. Dwarf planets were once dismissed as frozen fossils, lifeless remnants of the solar system's early days, but now they're stealing the spotlight as some of the most geologically surprising places we've ever discovered. Take Pluto, where the massive Wright Mons looms over the landscape like a frozen titan. This isn't just any mountain. It's a cryovolcano so large that if you stood at its base, the summit would vanish into the haze of Pluto's thin atmosphere. And it's not alone. Over on Ceres, the solitary dome of Ahuna Mons rises abruptly from the dwarf planet's cratered surface, its smooth slopes telling a silent story of slow, icy eruptions. Even distant Eris, nearly 3 times farther from the Sun than Pluto, shows hints of cryovolcanic flows in telescopic observations. What makes these discoveries so shocking is the sheer improbability of it all. These worlds are tiny. Pluto is just 1/6 the size of Earth, and they orbit so far from the Sun that sunlight is barely more than a faint star in their skies. Conventional wisdom said they should have cooled off billions of years ago, their interiors frozen solid. Yet here they are, pumping out eruptions that reshape their surfaces in real cosmic time. The implications are staggering. If something as small as Ceres, barely 900 kilometers wide, can stay geologically active, what does that say about the hidden engines powering these worlds? Scientists suspect 2 key culprits might be at work. First, subsurface oceans' vast, slushy reservoirs trapped beneath miles of ice, kept liquid by a mix of radioactive decay and antifreeze chemicals like ammonia. These hidden seas could act as pressure cookers, building up force until they blast through the crust in cryovolcanic outbursts. Second, residual heat from the dwarf planet's violent births might still linger, trapped like a cosmic slow cooker beneath their icy shells. When NASA, a New Horizons spacecraft, spotted complex terrain on Pluto with barely any impact craters, a telltale sign of recent resurfacing, it was clear something was churning beneath the ice, erasing geological scars almost as fast as they formed. But perhaps the most thrilling possibility is what this means for life. On Earth, wherever we find liquid water and energy, we find life even in the most extreme environments. If dwarf planets like Pluto or Ceres have subsurface oceans warmed by tidal forces or radioactivity, could those dark, briny depths harbor simple organisms? It's not as far-fetched as it sounds. Europa and Enceladus, icy moons with confirmed subsurface oceans, are already top candidates in the search for extraterrestrial life. Now, dwarf planets are joining that list, proving that even the smallest, coldest worlds might hold the ingredients for biology. Every new discovery peels back another layer of mystery. These aren't just inert rocks drifting in the void, they're dynamic worlds with their own stories to tell. And as we uncover more about their hidden geology, one thing becomes certain. When it comes to the solar system's surprises, size doesn't matter. The smallest worlds might just hold the biggest secrets. Pluto's Wright Mons isn't just another mountain, it's a frozen giant that defies logic. Rising nearly 5 kilometers high, this sprawling cryovolcanic complex dominates the landscape with a jagged, irregular silhouette that looks more like a collapsed cake than a traditional volcano. At its center lies a gaping depression, almost as if the ground itself sank after countless eruptions drained the slushy reserves beneath. But the real shocker. Its surface is eerily smooth, untouched by the bombardment of cosmic debris that scars most of Pluto's terrain. That pristine surface tells scientists something extraordinary. Wright Mons wasn't just active in the distant past, it might have erupted as recently as a few million years ago, a blink of an eye in geological time. So how does a tiny, frozen world like Pluto power such a massive cryovolcano? The answer might lie in an unlikely cosmic partnership. Pluto and its largest moon, Charon, are locked in a gravitational dance so tight they orbit a shared point in space, constantly tugging on each other like dancers in a slow-motion spin. That relentless pull could be flexing Pluto's interior, generating enough friction to melt pockets of ice deep below the surface. Another possibility is radiogenic heat energy released by the slow decay of radioactive elements like uranium and potassium, remnants of Pluto's violent birth over 4 billion years ago. These hidden heat sources might be the engines driving Wright Mons eruptions, proving that even the smallest worlds can pack geological surprises. The implications are staggering. If Pluto, a dwarf planet with barely 1% of Earth's mass, can sustain cryovolcanism, what does that say about other icy bodies in the Kuiper belt? Wright Mons isn't just a curiosity, it's a blueprint for understanding how dwarf planets evolve. Its oozing eruptions of nitrogen, methane, or water ice could even hint at a subsurface ocean, a hidden layer of liquid trapped beneath miles of ice, kept warm by the same forces fueling its volcanic tantrums. But here's the real kicker. Wright Mons might not be alone. New Horizons Fly by only captured one side of Pluto in detail, leaving vast regions unexplored. Could there be more cryovolcanoes lurking in the shadows, waiting to rewrite the story of this tiny world? Every unanswered question turns Pluto from a distant speck into a frontier of discovery, proving that in the cosmos, size means nothing when it comes to geological drama. Standing like a lonely sentinel in the vast emptiness of Ceres, Ahuna Mons defies expectations at every turn. This 4-kilometer tall mountain isn't just another bump on a dwarf planet's surface. It's a frozen time capsule of cryovolcanic activity, its steep slopes revealing secrets about the hidden forces shaping this tiny world. Unlike Pluto's Wright Mons with its sprawling volcanic complex, Ahuna Mons rises abruptly from Ceres' cratered plains with no neighbors in sight, making its existence even more puzzling. The Dawn spacecraft's close-up images tell a fascinating story. Those smooth, almost polished slopes weren't carved by impacts or erosion. They were built layer by layer from viscous eruptions of salty, muddy ice oozing upward in slow motion. Imagine not fiery lava, but a frigid slurry of water mixed with salts like magnesium sulfate bursting through Ceres' crust, then freezing into towering ridges over millions of years. What makes this even more remarkable is the timeline. Ahuna Mons might have erupted as recently as 200 million years ago. That sounds ancient to us, but in geological terms, it means this cryovolcano was active when dinosaurs roamed Earth, long after Ceres should have cooled into silence. Why is this mountain so alone? Ceres' surface shows no other obvious cryovolcanic structures nearby, sparking heated debates among planetary scientists. One compelling theory suggests tectonic activity might have buried older cryovolcanoes over time, with Ahuna Mons being the last survivor of a once vibrant geological era. Others speculate we're witnessing the final gasp of Ceres' internal heat, a single cryovolcano pushing through before the dwarf planet's engine shuts down completely. There's even a chance Ahuna Mons formed from a one-of-a-kind event, like a massive impact fracturing the crust and allowing subsurface brines to erupt in a singular, dramatic episode. But here's what truly excites researchers. Ahuna Mons might be the visible tip of an invisible ocean. Ceres shows clear signs of a global brine reservoir beneath its surface, and the mountain's composition, rich in salts that lower water's freezing point, hints at deep connections to this hidden liquid layer. Every eruption could have been a release valve for pent-up pressures in that subsurface sea, making Ahuna Mons not just a geological oddity, but a window into Ceres' inner workings. The deeper we look, the more questions arise. Why does Ceres have such concentrated cryovolcanism in one spot while other dwarf planets show more widespread activity? Could there be smaller, eroded cryovolcanoes we're missing? Each answer rewrites our understanding of how small, icy worlds evolve, and with NASA upcoming missions targeting Ceres, Ahuna Mons may soon surrender even more of its frozen secrets. Beneath the frozen crusts of distant dwarf planets, an astonishing secret might be lurking: vast, dark oceans, hidden for billions of years. These aren't the sunlit seas of Earth, but alien abysses sealed under miles of ice, where water remains liquid against all odds. Scientists now suspect that Pluto's heart-shaped glacier, Sputnik Planitia, could float atop such a subsurface ocean, explaining why this region sits suspiciously lower than its surroundings. Even Ceres, that tiny world in our asteroid belt, shows signs of briny reservoirs deep below its cratered surface. The mechanism keeping these oceans from freezing solid is as clever as it is unexpected natural antifreeze. Ammonia, salts like magnesium sulfate, and even methanol mix with water in these hidden seas, lowering their freezing points dramatically. Imagine pouring salt on an icy sidewalk to melt it. Now picture that same principle operating on a planetary scale, with chemistry preventing entire oceans from turning to stone. When cryovolcanoes erupt, they might be spewing samples of these antifreeze-laced waters into space, offering spacecraft a free taste of what lies beneath. That's exactly what happened on Saturn's moon Enceladus, where NASA Cassini probe flew through geyser plumes and detected organic molecules, the building blocks of life. Could Pluto or Ceres be doing the same? The implications for biology are electrifying. On Earth, life thrives in the most extreme places: boiling hydrothermal vents, acidic hot springs, even radioactive pools. Subsurface oceans on dwarf planets could provide similar niches: liquid water, chemical energy from hydrothermal activity, and protective ice shields against radiation. Europa, Jupiter's icy moon, is already a prime target in the search for alien microbes, but dwarf planets like Ceres might be even more accessible. Unlike the gas giants' moons, which orbit in punishing radiation belts, Ceres sits relatively close in the asteroid belt, making it a tantalizing pit stop for future missions. Yet the biggest challenge remains piercing through the ice. These oceans could be buried tens of kilometers deep, far beyond the reach of current drilling technology. That's where cryovolcanoes become invaluable. They're nature's own sampling tools, dredging material from the depths and delivering it to the surface. When New Horizons spotted possible cryovolcanic flows on Pluto, it wasn't just seeing geology, it was glimpsing potential delivery routes for ocean material. Future missions might land near these features, scooping up freshly erupted slush to analyze for hints of chemistry or even biology that could rewrite our definition of habitable worlds. The quest to find these hidden oceans is already shaping the next generation of space exploration. NASA Dragonfly mission will soon search for life on Titan, but proposals for Ceres landers and Pluto orbiters are gaining momentum, armed with drills, spectrometers, and seismic sensors designed to listen for sloshing waters beneath the ice. Every cryovolcano we discover isn't just a geological oddity. It's a potential roadmap to an ocean, a signpost pointing to where we should look next. And if one of these dark, briny depths holds even microbial life, it would prove that vitality isn't confined to warm, sunlit worlds. Life, it seems, might flourish in the unlikeliest of places, growing in eternal night beneath the ice of a dwarf planet, waiting for us to take notice. Gravity works in mysterious ways, especially when it comes to powering alien volcanoes. While Earth's fiery eruptions rely on internal heat, some of the solar system's most dramatic geology is fueled by something far more subtle: the relentless tug of tidal forces. Take Jupiter's moon Io, the most volcanically active place we know, where gravitational squeezing from the giant planet melts rock into lava that erupts in towering fountains. Or Europa, where tidal flexing likely keeps a global ocean sloshing beneath miles of ice. But here's the twist: dwarf planets don't orbit gas giants, so how could tidal heating possibly explain their cryovolcanoes? The answer lies in an unexpected cosmic dance. Pluto and its largest moon Charon are locked in a gravitational embrace so intimate they orbit a shared point in space, like two figure skaters holding hands while spinning. This constant push and pull doesn't just keep their surfaces locked in place, it flexes their interiors, generating friction that could melt pockets of ice deep underground. Even slight stretching over billions of years might be enough to maintain the slushy reservoirs that feed cryovolcanoes like Wright Mons. Other distant dwarf planets could have similar hidden partners, undiscovered moons, or even binary relationships with neighboring worlds that keep their geological engines churning long after they should have frozen solid. The math is mind-bending. For tidal heating to work, the gravitational pull needs to be just right, strong enough to generate internal friction, but not so violent it tears the world apart. In Pluto's case, Charon's grip is gentle but persistent, like slowly kneading dough. Each tiny deformation converts gravitational energy into heat, potentially creating isolated pockets of liquid beneath the ice. Over eons, that heat could build pressure until the crust cracks, allowing cryovolcanic eruptions to burst forth. It's a delicate balance, but one that might explain why Pluto's surface shows signs of surprisingly recent geological activity despite its tiny size and frigid environment. What's truly astonishing is the endurance of this process. Tidal heating isn't a short-lived phenomenon. It can persist for billions of years, as long as the gravitational dance continues. That longevity might be the key to understanding why some cryovolcanoes outlast all predictions. While radioactive decay slowly fades over time, tidal forces keep pumping energy into these worlds, offering a near-limitless power source for geological activity. Even after the solar system's birth heat dissipated and radioactive elements decayed, tidal flexing could have kept dwarf planets geologically alive, their cryovolcanoes erupting in slow motion across cosmic history. Yet mysteries remain. Why do some dwarf planets show clear signs of cryovolcanism while others appear dormant? Is tidal heating alone enough? Or does it need help from antifreeze chemicals or residual radioactivity? Every new discovery peels back another layer, like the recent detection of possible cryovolcanic domes on distant Eris, a dwarf planet with no known large moons. If tidal forces aren't at work there, what's keeping its engine running? The search for answers is pushing scientists to rethink the limits of planetary geology, proving that even in the coldest corners of space, gravity's subtle touch can shape worlds in spectacular ways. Deep beneath the icy crusts of dwarf planets, a silent powerhouse ticks away radioactive decay, the slow burn of the cosmos. Heavy elements like uranium, thorium, and potassium, forged in the violent deaths of ancient stars, pepper the interiors of these distant worlds. As these atoms split apart over billions of years, they release tiny bursts of heat, a faint but relentless warmth that might be the hidden engine behind some of the solar system's most mysterious eruptions. Take Ceres, for example. Those enigmatic bright spots scattered across its surface, glaring like cosmic headlights in spacecraft images. They're likely salt deposits, possibly left behind by briny water that bubbled up from deep below. But how does a small, frozen world like Ceres keep liquid water moving to the surface after billions of years? The answer could lie in radioactive decay's patient, persistent warmth. Unlike the dramatic tidal heating of moons orbiting gas giants, this process is more like a slow-burning ember, weak by itself, but over geological time, it's enough to melt pockets of ice into slushy reservoirs. When pressure builds, that slush might punch through the crust in cryovolcanic oozes, leaving behind salt plains as evidence of its journey. The math is staggering. A single kilogram of uranium, decaying over its 4.5 billion-year half-life, releases enough heat to warm a small bathtub of water for eons. Now imagine dwarf planets like Pluto or Ceres, their interiors sprinkled with radioactive material like raisins in a cosmic muffin. Even if only a fraction of their mass is made up of these elements, the collective warmth could be enough to maintain underground lakes or even global oceans beneath miles of ice. It's not the explosive energy of Earth's volcanoes, it's geology in slow motion, where eruptions might take millennia to build, and flows creep across the surface like frozen syrup. Yet the story isn't so simple. Radioactive decay alone might not explain the sheer scale of cryovolcanic features like Pluto's Wright Mons or Ceres' Ahuna Mons. Some scientists argue it's a team effort, radioactivity providing the baseline heat, while other mechanisms like tidal flexing or antifreeze chemistry amplify the effect. Others point to dwarf planets' chaotic early years, when collisions with other bodies could have concentrated radioactive materials in certain regions, creating localized hotspots ripe for cryovolcanism. What's clear is that these distant worlds are far from dead. They're dynamic, their surfaces reshaped by forces we're only beginning to understand. And with every new mission, every spectrometer reading, every high-resolution image, we get closer to unraveling the role of this hidden nuclear furnace in shaping the most unexpected corners of our solar system. Far beyond Pluto, in the frozen fringes of the Kuiper belt, the dwarf planet Eris drifts in near-total darkness, so distant from the Sun that a single orbit takes 557 Earth years. Yet this isolated world, colder than liquid nitrogen and barely warmed by starlight, might be hiding a geological secret that defies all logic. Recent observations reveal a surface suspiciously smooth, with patches so fresh they look newly polished, as if something erased the scars of cosmic impacts. The leading theory, cryovolcanoes, ice-spewing giants that could still be active today, painting Eris landscape in slow-motion eruptions. If true, this would rewrite the playbook on how tiny, frozen worlds generate enough heat to stay geologically alive. Eris isn't just any dwarf planet, it's the heavyweight champion of the Kuiper belt, 27% more massive than Pluto. That extra bulk should have locked away its internal heat eons ago, leaving it as inert as a cosmic snowball. Yet spectral data tells a different story. Its surface shows signs of nitrogen and methane ices that should have evaporated into space over millions of years unless replenished by fresh eruptions. Even more baffling are the bright, reflective regions near its equator, which resemble oozing flows seen on active moons like Europa. How could a body this small and cold possibly sustain such activity? One radical possibility involves exotic ice. At Eris crushing pressures and sub-zero temperatures, water molecules can rearrange into strange crystalline forms known as hot ices, which release heat as they transition between states. Imagine an iceberg that generates warmth simply by changing its internal structure, a self-heating geological battery that could power eruptions for billions of years. Another theory points to Eris' tilted orbit, which swings it wildly closer to the sun before retreating into the deep freeze. These extreme temperature swings might crack its icy shell, allowing buried gases to erupt in sporadic, explosive bursts. But the real shocker is what this means for our solar system models. If Eris, with no nearby moons to generate tidal heating and barely any sunlight, can stay geologically active, then countless other distant worlds might be secretly churning beneath their icy surfaces. Every unexplained patch of fresh ice, every oddly smooth plain, could be a clue pointing to hidden oceans, antifreeze chemistry, or energy sources we haven't even imagined. Eris isn't just a puzzle, it's a wake-up call proving that the outer solar system is far more dynamic than we ever dared to dream. Neptune's moon Triton is a cosmic chameleon, a world that shouldn't be this lively. Orbiting backward against its planet's rotation, this frozen outpost screams its origins as a captured dwarf planet, a wanderer from the Kuiper belt pulled into Neptune's gravitational grip. But what makes Triton truly extraordinary isn't just its rebellious orbit. It's the explosive geysers that blast nitrogen gas 8 kilometers high, painting its icy surface with dark streaks like cosmic graffiti. These aren't just geological oddities, they're a Rosetta Stone for understanding how dwarf planets, even those adrift in the void far from any star, might stay geologically active against all odds. Unlike the slushy eruptions on Pluto or Ceres, Triton's geysers run on sunlight, but not in the way you'd expect. At -235 degrees Celsius, the feeble warmth of the distant sun can't melt ice directly. Instead, it works like a slow cooker through a phenomenon called solid-state greenhouse heating. Sunlight penetrates Triton's translucent nitrogen ice, getting trapped beneath the surface like heat under a blanket. Over time, that energy builds until pockets of nitrogen gas explode upward, carrying dark dust from underground layers and creating eruptions so predictable they almost feel seasonal. It's cryovolcanism with a twist, a reminder that even in the solar system's darkest corners, simple physics can spark astonishing complexity. The implications for free-floating dwarf planets are staggering. If Triton, a captured world now tethered to Neptune, can muster this much activity, what about its untethered cousins in the Kuiper belt? Sunlight there is even weaker, but the same physics might apply on longer timescales, with radioactive decay or tidal stresses substituting for solar warmth. Telescopes have already spotted dwarf planets like Sedna with bizarrely reflective surfaces, hinting at ongoing resurfacing by frost or cryovolcanic flows. Triton proves the recipe works. Take an icy body, add a dash of energy, whether from sunlight, radioactivity, or gravitational tugging, and voila, you've got eruptions in deep freeze. But here's the real kicker: Triton's geysers might be a preview of something even wilder. Astronomers theorize some rogue dwarf planets, unbound to any star, could drift through interstellar space with subsurface oceans kept liquid by dark, slow-burning heat. If a captured world like Triton can stay lively, why not these lone wanderers? Every nitrogen plume on Triton is a message in a bottle, telling us that activity in the outer solar system isn't the exception, it's the rule. And as we peer deeper into the Kuiper belt, we might find that the coldest worlds are anything but frozen in time. Ahuna Mons on Pluto stands as one of the solar system's most perplexing cryovolcanic giants, a sprawling massif with a summit depression so vast it could swallow entire cities. Unlike the steep slopes of Earth's volcanoes, Ahuna's's gently undulating terrain hints at eruptions of ultra-viscous ice, oozing like cold honey across the dwarf planet's surface. Nearby, the smaller but equally mysterious Virgil Fosse sports fissures that may have once spewed liquid nitrogen, carving valleys as they froze almost instantly in Pluto's thin atmosphere. These aren't isolated oddities, they're part of a growing catalogue of 29 confirmed or suspected cryovolcanic sites across dwarf planets, each with its own geological fingerprint. Venture to Ceres, and the cryovolcanic story takes a saltier turn. Ahuna Mons might be the poster child, but scattered across this dwarf planet's surface lie dome-like features barely a few hundred meters tall, miniature cryovolcanoes built from briny mud that erupted in sluggish, frozen fountains. Their mineral-rich compositions, detected by NASA's Dawn spacecraft, suggest reservoirs of subsurface brine loaded with magnesium sulfate and carbonates, a cocktail that could lower the freezing point of water by dozens of degrees. Meanwhile, on distant Makemake, telescopic observations reveal unusually bright patches that might be fresh nitrogen or methane frost, possible evidence of cryovolcanic venting, replenishing the surface in real time. The diversity of these features is staggering. Some, like Pluto's Wright Mons, resemble shield volcanoes with gentle slopes formed by countless slow eruptions. Others, like the jagged peaks rumored on Haumea, could be explosive vents where methane or nitrogen gas blasted through the crust in violent outbursts. Even the eruption timescales vary wildly. While Ahuna Mons might have taken millions of years to form, Ceres' smaller domes could have built up in geologically brief spurts. This isn't just a list of curiosities, it's a cosmic laboratory, offering snapshots of how volatile chemistry, heat sources, and gravity shape worlds under wildly different conditions. What unites them is their defiance of expectations. These aren't relics of ancient activity, they're dynamic systems, some potentially still brewing beneath the ice. When New Horizons spotted glacial flows on Pluto's Sputnik Planitia, some no older than a few 100,000 years, it proved that cryovolcanism isn't a one-time event but an ongoing process. Similarly, Ceres' occasional haze, possibly water vapor escaping from recent eruptions, hints that even small bodies can stay geologically restless. Each entry in this catalogue pushes scientists to rethink the boundaries of planetary activity, proving that heat and chemistry can conspire in unexpected ways to keep even the coldest worlds alive. Yet for all we've mapped, the catalogue remains frustratingly incomplete. Eris' smooth plains hint at cryovolcanic resurfacing, but without close-up images, we're left guessing. Sedna's reddish tint could be organic compounds brought up by icy eruptions, but it orbits too far for confirmation. Every unanswered question is a reminder that these 29 sites are just the beginning, a preview of the geological dramas still waiting to be uncovered in the solar system's frozen frontier. The violence of an eruption isn't just about heat, it's a cosmic chemistry experiment playing out in ultra-slow motion. On Pluto, cryovolcanoes like Wright Mons ooze nitrogen-rich slurries across the surface, their flows creeping forward at speeds measured in centimeters per year. These are effusive eruptions, the geological equivalent of squeezing toothpaste from a tube, gradual, steady, and built layer by frozen layer. But cross the solar system to Neptune's moon Triton, and the rules change. Here, geysers blast nitrogen gas 8 kilometers high at nearly 400 kilometers per hour, creating explosive plumes that dwarf anything on Earth. The difference, it all comes down to what's mixing beneath the ice. gas content is the invisible puppeteer behind these eruption styles. On worlds like Pluto, where slushy water ice mixes with just a whisper of nitrogen or methane, eruptions tend to be viscous and slow. The limited gas acts more like bubbles in thick lava, barely nudging the material upward, but add too much volatile gas like the carbon monoxide suspected beneath Triton's crust, and you've got a pressure cooker waiting to blow. When cracks form in the ice, these trapped gases expand violently, shredding the surrounding slurry into fine particles and launching them skyward in umbrella-like plumes. It's the same physics that makes a shaken soda bottle erupt, just scaled up to planetary proportions. Ice composition plays an equally crucial role. Ammonia mixed with water creates a natural antifreeze, lowering melting points and allowing even sluggish eruptions in extreme cold. Salt-rich brines, like those erupting from Ceres' Ahuna Mons, flow more like thick pancake batter than water, building domes rather than spreading into flat plains. Meanwhile, the methane ice dominating Pluto's Sputnik Planitia behaves almost like a glacier on Earth, except at temperatures where nitrogen becomes the flowing agent, creating surreal landscapes of creeping ice lobes. Each mixture produces distinct eruption signatures, from the jagged ridges of water ice volcanoes to the smooth, rounded domes of salt and mud cryovolcanism. Pressure completes the trifecta. On small worlds with thin atmospheres like Ceres, erupted material meets little resistance, allowing even gentle oozes to spread widely before freezing. But on Pluto, where atmospheric pressure is just 100,000th of Earth's, nitrogen-rich slurries can vaporize instantly at the surface, creating temporary local atmospheres that rain back down as exotic frosts. The most extreme pressure swings occur when subsurface liquids encounter the vacuum of space, a scenario that might explain the explosive plumes spotted on Saturn's moon Enceladus, where water erupts so violently it reaches escape velocity, feeding one of Saturn's rings. These differences aren't just academic, they're roadmaps for future exploration. Effusive cryovolcanoes like Pluto's are time capsules, preserving layers of erupted material that record climate changes over millions of years. Their slow flows make them safe landing targets for probes seeking samples of subsurface chemistry. Explosive sites, however, offer instant access to deeper materials blasted high above the surface, perfect for fly-through missions like Cassini's daring plunges through Enceladus plumes. By reading the eruption styles scattered across the solar system, we're not just studying geology, we're learning where to look next in the search for alien oceans and perhaps life itself. The next frontier, worlds like Jupiter's moon Europa, where telescopic evidence suggests both explosive plumes and effusive flows, might coexist, a tantalizing hint that even within a single body, cryovolcanism can wear many faces. As our probes push farther into the icy reaches of the solar system, each new eruption style adds another piece to the puzzle, revealing the astonishing diversity of ways frozen worlds stay geologically alive. Deep beneath the frozen crusts of distant worlds, an invisible architect shapes some of the solar system's most violent eruptions, clathrates, crystalline cages of water ice that trap flammable gases like cosmic prisons. Picture a honeycomb structure where every tiny cavity holds a molecule of methane or carbon monoxide, locked away under extreme pressure. These aren't just geological curiosities, they're ticking time bombs capable of turning a sluggish cryovolcanic ooze into a catastrophic explosion with the right trigger. The physics at play is both elegant and terrifying. When heat from tidal flexing or radioactive decay penetrates layers of clathrate-rich ice, the cages begin to collapse, releasing their volatile prisoners in a sudden rush. Methane, normally inert in Pluto's frigid environment, becomes a potent fuel when concentrated, expanding rapidly as it transitions from solid to gas, fracturing the ice above like a hammer strike. This process might explain the bizarre, explosive geomorphology on Neptune's moon Triton, where dark streaks radiate from vents at velocities that defy the moon's weak gravity. Similar structures on dwarf planets like Eris could indicate buried clathrate deposits detonating in slow motion, their outbursts frozen in time by the vacuum of space. What makes clathrates so uniquely dangerous is their efficiency. Unlike traditional cryovolcanism, where heat must melt substantial volumes of ice to create pressure, clathrates amplify small temperature changes into disproportionate effects. A mere 5-degree shift might destabilize entire methane reservoirs, triggering chain reactions that propagate through the ice like falling dominoes. Some scientists speculate this could create cryovolcanic supereruptions, rare but catastrophic events where whole regions of a dwarf planet's surface shatter in weeks-long paroxysms, flinging ice chunks into orbital trajectories. The evidence is mounting when New Horizons photographed Pluto's Virgil Fossae, a series of jagged fissures surrounded by nitrogen ice flows. Researchers noticed peculiar pit chains aligned like shrapnel scars. These could be the aftermath of clathrate-driven explosions, where pressurized gases blew through the crust in a series of violent decompressions. Even Ceres' occasional haze, detected by the Dawn spacecraft, might originate from clathrate breakdowns venting methane through surface cracks. But the real revelation is how clathrates blur the line between geology and chemistry. On Earth, similar structures under ocean floors can destabilize without warning, causing underwater landslides and methane releases that impact global climate. On dwarf planets, that same instability might carve entire landscapes in a single violent episode, then lie dormant for millennia until the next thermal pulse. This isn't just volcanism, it's planetary alchemy, where ice and gas conspire to reshape worlds in ways we're only beginning to comprehend. The implications stretch far beyond our solar system. Exoplanets orbiting dim red dwarf stars, where surface temperatures hover near clathrate stability zones, could experience cryovolcanism on a scale we've never witnessed. Explosive eruptions fueled by cosmic chemistry rather than molten rock. Every plume we analyze, every fractured plane we map, brings us closer to understanding this hidden force that might shape not just dwarf planets, but ice worlds across the galaxy. Gravity holds an invisible brush, painting cryovolcanic landscapes in strokes that vary wildly across the solar system. On dwarf planets like Pluto and Ceres, where surface gravity is barely a fraction of Earth's, eruptions unfold in surreal slow motion. Cryolava, whether slushy water, nitrogen ice, or salty brine, doesn't just ooze, it sprawls. Without the strong pull of gravity to contain it, erupted material spreads outward in vast, pancake-like flows, creating gentle domes that stretch for miles rather than the steep, conical mountains we associate with terrestrial volcanoes. Wright Mons on Pluto exemplifies this. Its sprawling, flattened profile looks more like a collapsed soufflé than a traditional volcanic peak, a direct consequence of icy slurry creeping effortlessly across a low-gravity surface. But gravity's influence doesn't stop at shaping landforms. It transforms eruptions into aerial spectacles. When cryovolcanic material breaches the surface on a dwarf planet, the weak gravitational pull allows plumes to soar to astonishing heights. On Neptune's moon Triton, geysers of nitrogen gas shoot 8 kilometers into the sky, a feat impossible on larger worlds where gravity would drag the material back down almost immediately. Even on Ceres, where gravity is just 3% of Earth's, simulations suggest ancient cryovolcanic plumes could have lofted briny water high above the surface, where it froze into crystalline frost before drifting back down like extraterrestrial snow. The dynamics grow even stranger when you factor in explosive eruptions. On Earth, volcanic explosions are tempered by gravity's grip on ejected debris, limiting how far ash and rock can travel. But on a dwarf planet, the same explosive force could send debris arcing dozens of kilometers before landing, or even escape into space entirely. Imagine a methane clathrate detonation on Eris. With surface gravity just 1/12 of Earth's, the blast could propel ice chunks into orbits around the dwarf planet, creating temporary rings before the fragments slowly rain back down. Yet low gravity isn't just a spectacle maker, it's a preserver. On massive worlds, cryovolcanic flows would quickly collapse under their own weight, leaving behind crumpled, chaotic terrain. But dwarf planets' gentle gravity lets erupted material freeze in place, maintaining delicate structures for eons. Those bizarre, wrinkle-like ridges on Pluto's Sputnik planisher. They're likely nitrogen ice flows that solidified mid-creep, their intricate patterns preserved like cosmic fingerprints. Similarly, the smooth, uncratered plains around Ceres' Ahuna Mons suggest its muddy eruptions froze into pristine landscapes, untouched by the gravitational settling that would distort them on larger bodies. The lesson is clear. Gravity doesn't just dictate how cryovolcanoes erupt, it defines their very language. From the way plumes dance in thin atmospheres to the way flows solidify into otherworldly sculptures, every feature whispers secrets about the forces shaping these distant worlds. And as we uncover more cryovolcanic sites across the Kuiper belt, each one adds another verse to this gravitational poetry, proving that even the faintest tug of gravity can sculpt the solar system's most enigmatic landscapes. Every eruption on a frozen dwarf planet is more than just a geological event, it's an atmospheric rebirth. When cryovolcanoes spew their icy mixtures into the void, they don't just sculpt landscapes, they momentarily transform entire worlds with fleeting veils of gas. Take Pluto's haunting blue haze, a nitrogen-rich shroud that dances in sunlight 200 times dimmer than Earth's. This ethereal blanket isn't constant, it's a dynamic byproduct of cryovolcanic activity, with geysers like those near Sputnik planisher pumping fresh nitrogen into the sky even as solar radiation steadily strips it away. The result is a delicate balancing act, an atmosphere so thin you'd need nearly 500 Plutos worth of air to fill a single earthly breath, yet substantial enough to create winds that sculpt surface ices into dunes. The chemistry behind these temporary atmospheres is just as fascinating as their formation. On Ceres, Dawn spacecraft observations detected sporadic water vapor hovering above Arcata crater molecules that likely originated from briny eruptions deep within the dwarf planet. Unlike Pluto's nitrogen-dominated haze, Ceres' exhalations are salt-laced water vapor, bursting forth when subsurface reservoirs heated by radioactive decay find escape routes through cracks in the crust. These plumes don't linger long in the vacuum of space, but while they last, they create transient microclimates where frost can form and sunlight scatters through microscopic ice crystals. What makes these atmospheric whispers so valuable to scientists is their snapshot quality. Each eruption captures a moment in planetary evolution, like a single frame from a billion-year film. Pluto's atmospheric pressure fluctuates wildly, sometimes doubling in density as fresh nitrogen erupts, then dwindling as the gas escapes into space or condenses onto the surface as exotic frost. These cycles create layered ice deposits that act as climate archives, preserving records of cryovolcanic activity across millennia. Similarly, Ceres' occasional water vapor releases suggest an active interior still capable of punctuated outbursts, challenging assumptions about how quickly small bodies should cool. The implications stretch far beyond our solar system. If cryovolcanism can generate temporary atmospheres on dwarf planets, might the same process occur on icy exoplanets orbiting distant stars? Telescopes hunting for atmospheric signatures on small, cold worlds might actually be detecting cryovolcanic outgassing rather than permanent climate systems. Even more intriguing is the role these ephemeral atmospheres could play in transporting organic materials across planetary surfaces. Imagine nitrogen, winds on Pluto distributing methane snow, or water vapor plumes on Ceres carrying salts that could facilitate chemical reactions favorable for life. Yet these atmospheric ghosts are frustratingly elusive to study. Unlike the robust, continuous atmospheres of Earth or Venus, dwarf planet atmospheres wink in and out of existence, requiring perfect timing from orbiting spacecraft or Earth-based telescopes. When New Horizons raced past Pluto in 2015, it caught the dwarf planet mid-cycle, its atmosphere at a medium density. But what might we have seen if we'd arrived during a major cryovolcanic outburst? Future missions may need to loiter for years near these frozen worlds, waiting to catch their next atmospheric breath. Until then, each fleeting detection offers tantalizing clues about how even the smallest, coldest worlds can briefly cloak themselves in celestial whispers. At first glance, Earth's fiery Mount St. Helens and Pluto's icy Wright Mons couldn't seem more different. One blasts molten rock at temperatures hot enough to melt steel, while the other oozes slushy nitrogen at conditions colder than Antarctica's deepest ice. Yet these extremes share a universal truth. Whether fueled by scorching magma or freezing chemistry, volcanoes are nature's ultimate sculptors, reshaping worlds through forces that transcend temperature. The contrasts begin with their building blocks. Traditional volcanoes run on silicate rock, heated to over 1,000 degrees Celsius until it liquefies into runny basalt or sticky rhyolite. Cryovolcanoes, by comparison, deal in exotic ice's water laced with ammonia, methane, or nitrogen that flow at temperatures plunging below -200 degrees. Where Kilauea's lava races downhill at highway speeds, Pluto's cryolava creeps slower than growing tree roots, inching forward over centuries. Even their eruption styles diverge dramatically. While Earth's volcanoes explode with ash columns towering into the stratosphere, cryovolcanic outbursts often resemble slow-motion fountains, spraying slurries that freeze midair like instant snow. Yet beneath these surface differences lies a profound symmetry. Both systems rely on the same fundamental recipe: heat, pressure, and a pathway to the surface. On Earth, radioactive decay and residual planetary formation energy keep the mantle molten. On dwarf planets, tidal flexing or antifreeze chemistry creates pockets of liquid beneath the ice. In both cases, trapped volatiles, whether water vapor in magma or methane in cryolava, expand violently when pressure drops, driving eruptions through cracks in the crust. The physics is identical, only the ingredients change. The timescales of their activity reveal another striking parallel. Hawaii's Mauna Loa has been erupting intermittently for at least 700,000 years, a blink compared to cryovolcanoes like Ahuna Mons and Ceres, which likely built its slopes over millions of years. Yet both demonstrate geology's patience, the way planetary forces work in rhythms far slower than human lifetimes. Even their aftermaths mirror each other. Just as volcanic ash enriches Earth's soil, cryovolcanic deposits on Pluto leave behind nitrogen plains that may recycle into future eruptions, creating a slow-motion version of the rock cycle. What truly unites them is their transformative power. Olympus Mons on Mars and Wright Mons on Pluto stand as twin testaments to volcanism's ability to shape worlds, regardless of composition. One built the solar system's tallest mountain from hardened lava, the other crafted sprawling domes from frozen gases. Both processes recycle planetary interiors, release trapped volatiles, and crucially, create environments where chemistry can experiment with complexity. The same hydrothermal vents that might have nurtured Earth's earliest life could have icy counterparts beneath cryovolcanoes, where briny eruptions mix organics in subsurface oceans. This duality forces us to expand our definition of geological activity. A volcano isn't just a mountain that spews fire, it's any conduit where a world's inner energy finds escape. Whether that energy melts rock or liquefies ice matters less than what it reveals, that even in the universe's coldest corners, the same restless forces that built our planet are still at work, rewriting landscapes one frozen eruption at a time. The search for cryovolcanic activity doesn't end at the edges of our solar system, it's only just beginning. Imagine an exoplanet orbiting a dim red dwarf star so far away that its surface temperature hovers near absolute zero, where water ice is as hard as granite and methane flows like syrup. In these frozen realms, cryovolcanoes might erupt not with fiery lava, but with plumes of ammonia, nitrogen, or even exotic compounds we've yet to discover. While we haven't directly observed an extrasolar cryovolcano yet, the clues are stacking up. Planets like TRAPPIST-1H, a frigid world 7 times Earth's mass, could harbor subsurface oceans kept liquid by tidal heating prime conditions for icy eruptions. Others, like the rogue planet PSOJ 318, drifting untethered to any star, might rely on radioactive decay or residual formation heat to fuel their geological tantrums. Detecting these distant eruptions will require telescopes far more advanced than today's technology, but the blueprint already exists. When the James Webb Space Telescope analyzed the atmosphere of K218b, it found hints of water vapor, possibly from cryovolcanic outgassing. Future missions like the Habitable Worlds Observatory, set to launch in the 2030s, could spot the chemical fingerprints of cryovolcanic plumes, sudden spikes of methane, ammonia, or even complex hydrocarbons in an exoplanet's thin atmosphere. Another telltale sign: surface changes. Just as New Horizons mapped fresh ice flows on Pluto, next-generation telescopes might catch the glint of newly erupted frost on an exoplanet's surface, revealing where cryovolcanoes have rewritten the landscape. The real game-changer could be cryovolcanic seasonality. On moons like Enceladus, plumes vary in intensity based on orbital position, and the same might hold true for exoplanets. A world with a highly elliptical orbit could experience tidal flexing strong enough to trigger cryovolcanic outbursts during its closest approach to its star, then fall dormant as it retreats. By monitoring these cyclical changes, astronomers might pinpoint not just where cryovolcanoes exist, but when they're most active, yet the implications stretch beyond geology. If cryovolcanism can transport subsurface materials to an exoplanet's surface, it might also deliver the building blocks of life, salts, organic molecules, even liquid water, to environments where sunlight never reaches. A frozen world with frequent eruptions could essentially sprinkle its own surface with probiotic ingredients, creating pockets of habitability in the cosmic deep freeze. The search for extrasolar cryovolcanoes isn't just about cataloging geological curiosities, it's about tracing the hidden pathways that might lead us to life's next frontier. NASA Europa Clipper spacecraft, set to launch in 2024, isn't just another mission, it's a direct assault on one of the solar system's most tantalizing mysteries. Orbiting Jupiter's icy moon Europa, the Clipper will skim as close as 25 kilometers above its fractured surface, using radar to peer through miles of ice in search of subsurface lakes. But the real prize lies in its plume hunting tools. If Europa's cryovolcanoes are still active, spewing water vapor into space as suspected, the Clipper's mass spectrometers could catch molecules from its hidden ocean salts, organic compounds, even potential biosignatures without ever touching down. Imagine catching a snowflake from a blizzard and learning the entire ocean's chemistry from that single crystal. That's the Clipper's promise, a taste of Europa's depths delivered by its own eruptions. Meanwhile, proposals for a Pluto lander are gaining momentum, targeting the heart of cryovolcanic country. Picture a nuclear-powered probe touching down near Wright Mons, its drill penetrating the nitrogen-rich ice to sample layers deposited by ancient eruptions. Each frozen stratum would be a time capsule, preserving clues about Pluto's climate history and the composition of its potential subsurface ocean. But the boldest idea: a cryobot that could melt through the ice following the path of cryovolcanic plumes downward to search for liquid water and whatever might live there. These missions share a revolutionary approach, letting cryovolcanoes do the hard work. Instead of drilling kilometers through ice, why not study what the volcanoes themselves bring to the surface? Europa's plumes might deliver ocean material straight to spacecraft instruments, while Pluto's flows could offer frozen samples of its interior just centimeters below the dust. It's planetary science's version of catching a ride, hitching onto nature's own delivery system to explore places no probe could reach alone. The technological hurdles are staggering. Europa's radiation belts fry electronics, requiring the Clipper to make quick, precise passes through plume zones. A Pluto lander would face communication delays of over 4 hours each way, forcing it to navigate treacherous terrain autonomously. Yet the potential rewards justify the risk. Discovering amino acids in a cryovolcanic plume or detecting heat signatures from an active eruption could rewrite textbooks on where life might thrive. What makes these missions extraordinary isn't just their ambition, it's their timing. We're witnessing a golden age of cryovolcanic exploration, where spacecraft will soon study these phenomena at 3 wildly different worlds: Europa's salty jets, Pluto's slushy domes, and perhaps even Ceres' muddy eruptions. Each destination offers a unique laboratory to test theories about how cryovolcanoes work, and whether they're mere geological curiosities or lifelines to hidden biospheres. The answers won't just illuminate these frozen worlds, they'll reveal whether erupting ice is the universe's way of shouting its secrets into the void. Exploring cryovolcanic landscapes requires robots that can handle conditions tougher than any earthly extreme. Picture a rover attempting to climb the frozen slopes of Pluto's Wright Mons, where temperatures plunge below -230°C, cold enough to freeze batteries solid and turn rubber wheels brittle as glass. Or imagine a drone navigating the jagged fissures of Ceres' Ahuna Mons, where briny residue could gum up moving parts in seconds. These aren't hypothetical challenges, they're the real-world hurdles engineers face as they design the next generation of robotic explorers for icy worlds. Traditional Mars rovers like Curiosity rely on solar panels and heaters to survive, but cryovolcanic terrain demands radical reinvention. At Pluto's distance from the Sun, sunlight is 1,000 times dimmer than on Mars, rendering solar power nearly useless. Instead, missions like NASA proposed Pluto Hop, a nuclear-powered, leaping lander, would use radioisotope heaters to stay warm, while spring-loaded legs propel it across treacherous nitrogen ice fields. Meanwhile, for Europa's explosive plumes, engineers are testing fly-through drones equipped with ice-resistant coatings, capable of sampling geyser particles mid-eruption before retreating to safer altitudes. The real innovation lies in subsurface probes. Cryobots' cylindrical melt probes packed with heated drills could tunnel through miles of ice, following the paths of ancient cryovolcanic vents to reach hidden oceans. A prototype called Spindle, already tested in Antarctica, uses a hot tip to melt downward while leaving a communications cable trailing behind. On worlds like Enceladus, such bots might navigate by detecting temperature gradients, homing in on the warmth of active vents where microbial life could thrive. Yet mobility remains the ultimate challenge. Icy surfaces vary wildly from Pluto's rubbery nitrogen glaciers to Ceres' salt-crusted domes, requiring adaptable locomotion. Some concepts borrow from nature, snake-like robots that slither through crevices, or spider-inspired climbers with ice-gripping microspikes. Others sound like sci-fi. Ice screws that rotate into frozen slopes like self-drilling anchors, or balloon-tired rovers that distribute weight to avoid sinking into slushy terrain. The stakes couldn't be higher. Every robot that conquers these extremes brings us closer to answering whether cryovolcanoes are merely geological wonders or conduits to life's hiding places in the cosmic deep freeze. The moment we send a probe to explore an icy world like Europa or Enceladus, we face a paradox. Our quest to discover alien life could accidentally destroy it. Earth's toughest microbes, capable of surviving extreme cold, radiation, and even the vacuum of space, might hitch a ride on spacecraft, stowing away in microscopic crevices or hiding inside instruments. If those hardy organisms reached a subsurface ocean, they could thrive in the very environments we're searching for life, contaminating them forever. This isn't science fiction, it's a real dilemma that keeps planetary scientists awake at night, forcing them to weigh the risks of exploration against the irreversible consequences of human interference. Current sterilization protocols are rigorous but imperfect. NASA's Viking missions to Mars in the 1970s baked landers at over 100 degrees Celsius for days, a standard that's since been relaxed for non-life detection missions. The problem: some extremophiles, like Deinococcus radiodurans, can withstand radiation doses 1,000 times stronger than what would kill a human, and certain strains of bacteria have revived after being frozen for millions of years in Antarctic ice. Even the clean rooms where spacecraft are assembled aren't sterile. They're just clean enough to meet statistical probabilities of minimal contamination. For icy moons with potential subsurface oceans where liquid water could transport Earth microbes across entire worlds, those odds might not be good enough. The debate splits the scientific community. One camp argues for aggressive sterilization, even if it limits mission capabilities. They propose enclosing drills or cryobots in disposable, sterile sheaths that peel away after penetrating the ice, or using lasers to vaporize spacecraft surfaces before landing. Others counter that the search for life requires instruments too sensitive to survive such harsh treatments. A mass spectrometer analyzing organic molecules, for instance, can't function if its own components are baked into oblivion. Compromises exist, like targeting safe zones away from suspected plumes or designing probes that self-destruct after collecting samples. But each solution carries trade-offs that could delay discoveries by decades. Ethically, the stakes couldn't be higher. Contaminating a subsurface ocean wouldn't just muddy scientific data, it could erase the very signatures of alien life we're seeking, or worse, trigger ecological chaos in a pristine ecosystem. Imagine if Earth's oceans had been seeded with foreign microbes billions of years ago, altering the course of evolution before native life could emerge. At the same time, excessive caution might mean missing the chance to detect life altogether, leaving humanity forever wondering if we're alone. The Outer Space Treaty of 1967 obligates nations to avoid harmful contamination, but enforcement is murky, especially as private companies enter planetary exploration. Future missions are walking this tightrope in real time. Europa Clipper will orbit Jupiter's moon at a safe, distance, minimizing contamination risk while still studying plume material. A proposed lander, however, would need to touch down, and that's where the ethical calculus gets thorny. Some scientists suggest treating icy moons like Antarctica's protected lakes, where drills must stop short of penetrating fully into liquid water to preserve their purity. Others advocate for minimal viable contamination, accepting some risk to advance knowledge. As we push deeper into the solar system's frozen frontiers, one thing is clear: exploring these worlds demands more than technological brilliance. It requires humility, restraint, and the wisdom to recognize that some lines once crossed can never be uncrossed. Arthur C. Clarke saw it coming decades before scientists confirmed it. Cryovolcanoes erupting on distant worlds, their icy plumes hinting at secrets beneath the surface. In his novel 2010, Odyssey 2, Jupiter's moon Europa wasn't just a frozen wasteland but a geologically active enigma, its fractures spewing water into space. Clarke imagined these eruptions as portals to a hidden ocean, a concept so prescient it predated NASA discoveries by 30 years. Today, that blend of science and speculation has cemented cryovolcanoes as staples of sci-fi world-building, their otherworldly mechanics offering storytellers a canvas for the extraordinary. Modern films like Europa Report and the Cloverfield Paradox have leaned into their eerie potential, depicting cryovolcanic landscapes as both haunting and hospitable gateways to subterranean realms where alien ecosystems might thrive. The visuals alone are irresistible: geysers of nitrogen ice glittering under starlight, methane slush cascading down obsidian black slopes, or plumes refracting sunlight into rainbows across a moon's thin atmosphere. But the real genius lies in how these fictional portrayals parallel real scientific debates. When Avatar: The Way of Water introduced bioluminescent cryovolcanic vents on Pandora, it echoed actual theories about hydrothermal systems beneath Europa's ice, environments where Earth's extremophiles flourish without sunlight. What makes cryovolcanoes such potent narrative devices isn't just their spectacle, but their duality. They're both destructive and creative, capable of obliterating terrain while seeding it with the ingredients for life. In The Expanse, the protomolecule's transformation of Venus begins with cryovolcanic upheaval, a metaphor for rebirth through chaos. Video games like Mass Effect and No Man's Sky use them as loot-rich exploration zones where players harvest exotic minerals from frozen lava flows. Even horror taps into their isolating menace. Films like Europa imagine cryovolcanic caves as labyrinths where ancient organisms lie dormant, waiting for unsuspecting explorers to trigger their awakening. Yet the most fascinating twist is how fiction often outpaces reality. Long before New Horizons spotted Pluto's Wright Mons, novels like Kim Stanley Robinson's 2312 depicted cryovolcanic terraforming, with humans harnessing their energy to melt icy moons for colonization. Others, like Project Hail Mary, weave hard science into the drama, using cryovolcanic chemistry as plot devices, alien life forms dependent on ammonia eruptions, or civilizations building cities atop geothermal vents. These stories aren't just entertainment, they're thought experiments challenging scientists to ask, if we found plumes on Enceladus, what else might we find? The line between inspiration and discovery blurs here. Clarke's fictional Europa became NASA a priority target because his vision was rooted in plausible physics. Now, as we stand on the verge of probing these icy worlds for real, cryovolcanoes symbolize something greater, a bridge between human curiosity and cosmic truth. They remind us that the universe's most alien landscapes might not just host life, but inspire the stories that drive us to seek it. Most people hear Ice Volcano and picture a frozen version of Mount Vesuvius, same explosive drama, just with frost instead of fire. But the reality is far stranger. Cryovolcanoes aren't just cold knockoffs of their fiery cousins. They're a completely different breed of geological phenomenon, operating under rules that seem almost alien compared to Earth's lava-spewing mountains. Take their plumbing systems for starters. Traditional volcanoes rely on molten rock rising through rigid silicate crust, creating the classic cone-shaped peaks we recognize. Cryovolcanoes, by contrast, often form in ice shells so flexible they behave more like putty than solid ground. When pressure builds beneath Pluto's surface, the overlying nitrogen and water ice don't fracture cleanly. They stretch and warp, creating sprawling domes like Wright Mons that look more like melted wax than steep volcanic edifices. Even the lava itself is unrecognizable. Instead of scorching basaltic flows, cryovolcanic eruptions might produce slurries of ammonia water antifreeze or methane slush that ooze at temperatures where earthly volcanoes would have frozen solid billions of years ago. The energy sources fueling these eruptions upend expectations too. While Earth's volcanoes tap into heat from radioactive decay and leftover planetary formation energy, cryovolcanoes often run on bizarre cosmic chemistry. Clathrate hydrates ice cages trapping flammable gases can explode when disturbed, launching plumes of material into space without any traditional heat input. On Triton, sunlight-penetrating translucent nitrogen ice triggers subsurface greenhouse effects, creating geysers in conditions colder than liquid nitrogen. These aren't just geological processes, they're lessons in how the universe repurposes basic physics in ways we're only beginning to decode. Perhaps the most persistent myth is that cryovolcanic eruptions are sluggish affairs, lacking the spectacle of terrestrial volcanoes. Tell that to the 8-kilometer high nitrogen geysers on Triton, which erupt at speeds rivaling jet aircraft. Or consider Ceres' mysterious bright spots, likely salt deposits from briny cryovolcanic outbursts which spacecraft observed forming in near real time. The violence isn't always fiery, but it's no less transformative. When methane clathrates beneath Eris surface destabilize, they might shatter entire landscapes in explosions that fling ice chunks into orbit. These differences aren't academic nitpicking, they're why studying cryovolcanoes demands entirely new toolkits. Traditional seismometers designed for rocky worlds fail in icy terrains where vibrations dampen quickly. Spectrometers must hunt for ammonia or methanol signatures instead of familiar silicate minerals. Even landing probes face unprecedented challenges, as wheels meant for Martian sand would sink into nitrogen slush or freeze solid in cryovolcanic frost. Every misconception corrected opens doors to sharper questions. If we've been wrong about how these eruptions work, what else might we have missed about the hidden engines powering our solar system's most surprising worlds? The irony is delicious. By assuming cryovolcanoes were just frosty copies of Earth's volcanoes, we underestimated their creativity. Nature didn't settle for cold imitations. It invented an entirely new form of geology. And in doing so, it handed scientists a gift, a reminder that the universe always has fresh surprises waiting for those willing to question their assumptions. Pluto's dramatic elliptical orbit isn't just a celestial quirk. It's the heartbeat of a frozen world, pulsing with geological consequences. Every 248 years, this dwarf planet swings from a frigid 30 astronomical units from the Sun to a slightly less bitter 49, a seasonal roller coaster that may crack its icy shell wide open. Picture this: as Pluto inches closer to the Sun, weak sunlight creeps across its nitrogen glaciers, warming them just enough to expand. That subtle thermal flexing could be the trigger for cryovolcanic chaos, fracturing the crust like an overfilled ice cube tray and unleashing pent-up slush from reservoirs below. These aren't random eruptions, they're celestial clockwork, tied to orbital rhythms that unfold over centuries. But Pluto's not alone in this seasonal symphony. Take Neptune's moon Triton, where the slow march of its polar seasons, each lasting 80 Earth years, drives geyser activity to explosive extremes. When the sun finally graces Triton's south pole after decades of darkness, its faint warmth penetrates translucent nitrogen ice, vaporizing trapped gases until they erupt in kilometer-high plumes. It's a reminder that seasonal cryovolcanism isn't about raw heat, but precision timing, a delicate balance where even minuscule temperature swings can leverage volatile chemistry into spectacular outbursts. The mechanics behind these eruptions read like a cosmic Rube Goldberg machine. On dwarf planets like Eris or Makemake, where orbits are even more extreme, subsurface ices like methane clathrates may undergo phase changes as temperatures fluctuate. Expand just a fraction during a warmer orbital phase, and suddenly you've got enough pressure to rupture ice caps that have held firm for millennia. Even Ceres, tucked in the asteroid belt, shows hints of seasonal activity. Its occasional water vapor plumes seem to coincide with periods when its axial tilt maximizes sunlight on frozen polar deposits. What makes these climate-driven eruptions so fascinating is their potential as planetary barometers. The layers within cryovolcanic domes could preserve a chronological record of orbital changes, much like tree rings document Earth's climate history. A thick layer of nitrogen-rich ice might correspond to an orbital perihelion, while a band of methane frost could hint at a particularly intense seasonal thaw. Future missions might literally drill into these timelines, decoding how dwarf planets respond to the subtle gravitational nudges that shape their orbits over eons. Yet the grandest implication isn't geological, it's biological. If seasonal cryovolcanism can fracture ice shells and eject subsurface material into space, it might also transport life's building blocks between layers. Imagine microbial spores frozen deep within a dwarf planet's crust, hitching a ride on a seasonal plume to reach sunlight-starved surfaces, or vice versa. The same orbital dances that trigger eruptions could be shuffling the cosmic deck, dealing fresh opportunities for chemistry to experiment with complexity in the unlikeliest of places. As telescopes peer deeper into the Kuiper belt, they're spotting more dwarf planets with wildly elliptical orbits, each potentially hosting its own version of this cryovolcanic rhythm. The lesson is clear: in the outer solar system, climate isn't just about weather. It's a geological force cracking open worlds to reveal the hidden engines beneath their icy skins. Scientists are now recreating alien worlds inside high-tech laboratories, using machines that mimic the extreme conditions of distant dwarf planets. In a facility at NAS, a jet propulsion laboratory, stainless steel chambers chill to -200 degrees Celsius while robotic arms inject precise mixtures of water, ammonia, and nitrogen under crushing pressures. These aren't just experiments, they're time machines, allowing researchers to witness cryovolcanic eruptions that would take millennia to unfold naturally. One groundbreaking simulation revealed how methane clathrates ice-like compounds trapping flammable gases can destabilize explosively when temperatures fluctuate by just 5 degrees, a finding that explains the bizarre pit chains spotted on Pluto's surface. Meanwhile, supercomputers crunch numbers at scales once thought impossible, modeling tidal forces on Europa or heat diffusion through Ceres crust down to the meter. Advanced algorithms can now simulate how a subsurface ocean might percolate upward through fractures over millions of years, or predict where future eruptions might scar a dwarf planet's surface. When paired with real-world data from missions like New Horizons, These digital laboratories become crystal balls, helping scientists retrodict past eruptions while forecasting where to aim cameras on upcoming flybys. The synergy between models and missions is rewriting textbooks. After dawn, spacecraft observations detected unexplained haze over Ceres. Lab experiments identified a plausible culprit: briny water erupting through surface salts, creating temporary atmospheres that vanish within hours. Similarly, when thermal models suggested Pluto's Sputnik Planitia glacier should have flattened over time, eruption simulations showed how periodic nitrogen geysers could replenish its rugged surface. Each discovery feeds back into the models, creating an ever-sharpening picture of how these frozen worlds operate. What makes this era revolutionary isn't just the technology, it's the paradigm shift. Cryovolcanism was once considered a niche curiosity, but these tools reveal it as a universal process shaping icy bodies across the solar system and beyond. The same physics powering Pluto's ice volcanoes might drive eruptions on exoplanets orbiting red dwarfs, where tidal forces squeeze frozen worlds into geological hyperactivity. Laboratories are already testing exotic scenarios, like nitrogen-methane mixtures under the gravitational pull of a super-Earth, or how silica-rich ices might behave in rogue planets untethered to any star. The next frontier lies in artificial intelligence's ability to spot patterns humans might miss. Machine learning algorithms recently trained on Cassini's Enceladus plume data identified previously overlooked eruption rhythms tied to orbital position, a discovery that could help predict outbursts on dwarf planets. Other AI systems analyze spectral fingerprints from ground-based telescopes, flagging subtle changes in surface composition that might signal fresh cryovolcanic deposits on distant Kuiper belt objects. Yet for all their sophistication, these tools raise as many questions as they answer. Why do some simulated eruptions match spacecraft observations perfectly while others veer wildly off course? Could unknown ice phases or exotic antifreeze compounds be tilting the equations? Every discrepancy is a clue pointing toward deeper complexities, lurking beneath the ice reminders that nature always has surprises waiting beyond the edges of our models. This convergence of computation and exploration marks a turning point. We're no longer just passive observers of cryovolcanism. We're becoming active participants in unraveling its mysteries, with laboratories serving as bridges between the solar system's frozen frontiers and the supercomputers decoding their secrets. The ultimate goal: to stand on the virtual surface of an undiscovered dwarf planet, watching simulated ice volcanoes erupt, and know with certainty that somewhere in the darkness, their real counterparts are doing the same. Imagine a classroom where students slip on VR headsets and suddenly stand on the jagged slopes of Pluto's Wright Mons, watching nitrogen slush ooze from fissures in hyper-realistic slow motion. Or a science fair where teens assemble tabletop cryovolcano models using dry ice and corn syrup to simulate the explosive chemistry of Triton's geysers. This isn't sci-fi, it's the cutting edge of STEM education, where the mysteries of distant ice volcanoes are becoming tangible experiences for the next generation of explorers. Museums and universities are collaborating to transform raw mission data into interactive exhibits, letting kids manipulate 3D terrain maps of Ceres' Ahuna Mons or adjust variables like gravity and ice composition to see how eruptions change on different worlds. The magic lies in making the incomprehensible familiar. When middle schoolers build edible cryovolcanoes with chocolate syrup, lava, freezing instantly in liquid nitrogen, they're not just memorizing facts, they're internalizing why Pluto's eruptions differ from Earth's. Apps like NASA Eyes on the Solar System let students pilot virtual probes through Europa's hypothetical plumes, collecting spectral data while learning orbital mechanics. Even board games have joined the movement. One popular title tasks players with managing a cryovolcanic research outpost, balancing resources to survive ammonia avalanches and methane storms. Teachers report breakthroughs when abstract concepts become visceral. A 7th grader who struggled with phase diagrams suddenly grasped them after watching a VR simulation of water-ammonia mixtures erupting under varying pressures. High school robotics teams now design miniature cryobots to navigate mock icy terrain, mirroring real engineering challenges faced by JPL scientists. The key is accessibility. Tools like Google's VR tour of New Horizons' Pluto Fly. I require nothing more than a smartphone and cardboard viewer, bringing cryovolcanic landscapes to schools without million-dollar budgets. Universities are taking it further with mission simulations where undergrads analyze datasets from actual cryovolcanoes. At Arizona State School of Earth and Space Exploration, students use AI tools to spot eruption patterns in Ceres surface spectra, mirroring professional research workflows. Some programs even partner with scientists. When the Europa Clipper team needed help classifying plume imagery, they crowdsourced undergrad analyses through a classroom partnership. These initiatives don't just teach science, they demystify the scientific process itself, showing that discovery isn't reserved for elite institutions. The ripple effects are profound. After a Colorado elementary school integrated cryovolcanoes into their geology unit, they tracked a 20% increase in girls expressing interest in planetary science careers. A teen from rural Alaska credits a VR encounter with Pluto's glaciers for her now ambition to study astrobiology. As education evolves from textbooks to immersive experiences, cryovolcanoes have become gateway features, their otherworldly allure sparking curiosity that cascades into broader STEM passion. The ultimate lesson that the universe's most alien phenomena aren't beyond comprehension, they're invitations to explore. Capturing cryovolcanoes on camera is like trying to photograph a snowstorm at midnight with a flashlight, except the snowstorm is on a distant world, the flashlight is a dying star, and the camera had to survive decades in deep space. The challenges begin with lighting. At Pluto's distance, sunlight is nearly 1,000 times dimmer than on Earth, turning what should be dramatic geological features into faint, low-contrast smudges. Add to that the reflective chaos of icy surfaces, where nitrogen frost and methane snow scatter light unpredictably, and you've got a nightmare scenario for imaging specialists. Yet against these odds, spacecraft like New Horizons have returned breathtaking vistas of cryovolcanic giants like Wright Mons, their wrinkled slopes etched in surreal clarity. These aren't just pretty pictures, they're triumphs of ingenuity, each pixel hard-won through a combination of cutting-edge engineering and meticulous planning. The secret lies in adaptive optics and painstaking exposure strategies. New Horizons' Long-Range Reconnaissance Imager, or LORI, functioned like the ultimate space camera, equipped with a telescopic lens sensitive enough to spot surface details under illumination equivalent to twilight on Earth. But even LORI needed help. To enhance contrast on Pluto's subtly shaded terrain, mission planners programmed the spacecraft to take multiple overlapping shots at different exposure levels, later merged into composite images on Earth. This technique, akin to high dynamic range photography, revealed textures invisible in single frames, like the faint flow lines radiating from cryovolcanic vents or the delicate layering in ice deposits. Timing was another hurdle, with New Horizons hurtling past Pluto at 14 kilometers per second. Every photographic opportunity was a split-second ballet. Cameras had to precisely track their targets while compensating for the spacecraft's motion, a feat requiring clockwork coordination between onboard computers and navigational thrusters. The payoff came in stunning revelations, high-resolution close-ups of Ahuna Mons' fractured summit, where icy eruptions once bubbled to the surface, and sweeping panoramas of Sputnik Planish's glacial plains, reshaped by cryovolcanic resurfacing. These images didn't just document geology, they transformed Pluto from a blurry dot into a world teeming with personality and dynamism. The color palette of cryovolcanic landscapes added another layer of complexity. Pluto's surface is a patchwork of muted reds, blues, and whites, a far cry from the fiery oranges of terrestrial volcanoes. To capture these subtleties, New Horizons' Ralph spectrometer mapped composition alongside visible light images, allowing scientists to later paint accurate hues onto black and white high-res shots. The result, ethereal portraits where methane-rich areas glow rusty brown against nitrogen's pale blues, revealing how different cryolavas mix and flow across the surface. Yet perhaps the most underappreciated challenge was data itself. Every high-resolution image consumed precious bandwidth during the agonizingly slow transmissions from the Kuiper belt. At Pluto's distance, a single megabit of data took over 4 hours to reach Earth, forcing mission planners to prioritize which cryovolcanic features deserved precious kilobytes. Some images arrived in fragments over months, like cosmic jigsaw puzzles slowly revealing their secrets. The legacy of these photographic triumphs extends far beyond Pluto. Lessons learned are shaping future missions to Europa and Enceladus, where cryovolcanic plumes demand even faster shutter speeds to freeze particles blasting into space. Proposed orbiters might deploy light buckets, ultra-sensitive sensors that gather photons over extended periods to tease out details in permanently shadowed regions. Meanwhile, AI-driven image processing now helps reconstruct faint surface features from noisy data, pushing the boundaries of what distant cameras can reveal. What makes these images extraordinary isn't just their technical achievement, it's how they've redefined our cosmic perspective. A single frame of cryovolcanic terrain can upend textbooks, proving that geology doesn't stop at the frost line. And as newer probes venture farther into the icy reaches of our solar system, their cameras will continue turning mathematical probabilities into visceral realities, transforming abstract hypotheses into landscapes we can wander with our eyes, one painstaking pixel at a time. The study of cryovolcanoes isn't just a scientific endeavor, it's a testament to what humanity can achieve when curiosity transcends borders. Take the New Horizons mission to Pluto, where American engineers worked alongside Japanese spectroscopists to decode the chemical fingerprints of Wright Mons eruptions, while European astronomers adjusted ground-based telescopes to track atmospheric changes caused by the dwarf planet's plumes. This wasn't just parallel research, it was a synchronized dance of shared data, with discoveries from one team informing the next in real time. When the spacecraft's images revealed possible cryovolcanic flows, scientists from 6 countries immediately collaborated to model how nitrogen-rich slush could ooze in Pluto's weak gravity, each bringing unique expertise to the puzzle. This global effort extends far beyond a single mission. The European Space Agency's JUICE probe, set to explore Jupiter's icy moons in the 2030s, carries instruments designed by U.S., Japanese, and Israeli researchers specifically to study cryovolcanic plumes. Meanwhile, Russia's proposed Venera D lander includes plans to test cryovolcanic detection tech that could later be adapted for icy worlds. Even nations without space programs contribute. Chilean astronomers use the high-altitude ALMA array to monitor distant dwarf planets for eruption signatures, while Indian supercomputers simulate tidal heating in Kuiper belt objects. The result is a scientific ecosystem where breakthroughs in one lab can trigger revelations halfway across the globe. What makes this collaboration extraordinary isn't just the sharing of data, it's the merging of perspectives. Japanese researchers approaching cryovolcanism through material science might spot structural patterns in ice fractures that American geologists overlook, while Brazilian chemists could recognize exotic antifreeze compounds based on their work in Amazonian extremophiles. When China's Chang missions discovered unexpected volatiles in lunar regolith, it sparked a re-evaluation of how ices behave on airless bodies, insights now applied to cryovolcanic models from Ceres to Eris. The International Astronomical Union's Cryovolcanism Task Force, with members from 34 countries, meets virtually every month to debate findings in 7 languages, proving that scientific progress has no native tongue. The challenges these teams overcome reveal collaboration's true value. Budget cycles, political tensions, and even time zones complicate coordination, yet the science persists. During the pandemic, when lockdown stalled NASA Europa Clipper assembly, German engineers shared 3D printed part designs that kept testing on schedule. When India's Mangalyaan orbiter spotted possible frost deposits near Martian volcanoes, its data was cross-referenced with ESA's Mars Express archives within hours, thanks to open-access databases. This isn't just efficiency, it's a shared acknowledgement that cryovolcanoes, like all planetary phenomena, belong to no single nation. They're cosmic mysteries demanding humanity's collective intellect. Perhaps the most profound impact of this teamwork lies in education. Students in South Africa analyze Pluto's cryovolcanic terrain using the same NASA datasets as researchers at Caltech, while joint field studies in Iceland's ice caves, where international teams simulate cryovolcanic environments, train the next generation of planetary scientists. When Chile's Atacama Desert hosts mock missions to test drill designs for Europa, participants from 15 countries learn to troubleshoot equipment together, forging partnerships that will define future exploration. The lesson is clear: understanding these icy eruptions requires more than advanced technology. It needs a unity of purpose that bridges continents. As missions grow more ambitious, cooperation becomes not just beneficial but essential. No single nation can fund a lander to Pluto's cryovolcanic plains or an orbiter mapping Eris' potential plumes, but together, pooling resources and expertise, these dreams inch toward reality. The proposed interstellar probe, a multinational effort to venture beyond the Kuiper belt, includes cryovolcanic studies in its core objectives, recognizing that the farthest reaches of our solar system hold clues to processes shaping icy worlds across the galaxy. In an era where earthly divisions often dominate headlines, cryovolcanology offers a counterpoint, a reminder that some questions are so profound they can only be answered by looking outward together. Beneath the frozen plumes of distant cryovolcanoes, an audacious possibility lingers. What if these erupting slush piles aren't just geological curiosities, but cosmic incubators? On Earth, life clings to the most unexpected niches, from boiling hydrothermal vents to Antarctic brine lakes sealed under kilometers of ice. The microbes thriving in these extremes, known as extremophiles, rewrite the rules of habitability daily. Now, imagine a similar scenario unfolding in the nitrogen-rich eruptions of Pluto's Wright Mons or the briny geysers of Ceres environments where liquid water, chemical energy, and organic compounds might briefly intersect in the cryovolcanic chaos. This isn't mere speculation. It's a frontier of astrobiology that's reshaping how we search for life beyond Earth. The chemistry of cryovolcanic fluids could be far more hospitable than their frigid temperatures suggest. On Enceladus, Saturn's icy moon, plumes erupting from a subsurface ocean contain salts, silica nanoparticles, and even molecular hydrogen ingredients that, on Earth, fuel entire ecosystems without sunlight. Dwarf planets might offer similar recipes. When Ceres' Ahuna Mons spewed salty mud, it could have carried not just minerals but prebiotic molecules like amino acids or lipids, forged in the warm depths below. Pluto's nitrogen glaciers, constantly churned by geothermal heat and cosmic radiation, might act as chemical reactors, shuffling simple compounds into more complex arrangements over millennia. The key isn't perpetual warmth, it's transient liquid water, a phenomenon cryovolcanoes provide in fleeting but recurring pockets. Timing is everything. Microbial life on Earth demonstrates astonishing resilience, surviving freeze-thaw cycles by producing natural antifreeze proteins or entering dormant states. On a dwarf planet, organisms, if they exist, might awaken during brief eruptive phases, metabolizing chemicals like methane or hydrogen sulfide before retreating into suspended animation when the slush refreezes. Europa's proposed chaos terrains, where ice collapses over subsurface lakes, hint at how such cycles could create habitable windows. Cryovolcanoes might operate similarly, offering periodic access to both liquid water and surface-derived organics blasted into space by impact. The implications for mission design are profound. Scientists crafting instruments for Europa Clipper or proposed Pluto landers now prioritize a plume chasing, a sampling ejected material for biosignatures like lipid membranes or genetic analogs. Even subtle hints like skewed ratios of amino acid isomers or unusual isotope patterns in methane could signal biological activity. The challenge lies in distinguishing between life's fingerprints and abiotic chemistry. A single detection won't suffice. Consistency across multiple eruption samples, paired with contextual data about energy sources, will be essential. Yet the boldest idea isn't just finding life, it's the possibility that cryovolcanoes could spread it. Panspermia, the theory that organisms hitchhike between worlds on meteorites, gains new traction when considering explosive eruptions. A cryovolcanic plume on Enceladus reaches escape velocity, seeding Saturn's E-ring with potential microbes. Could dwarf planets with their weaker gravity achieve similar feats? A high-energy eruption on Eris might launch ice grains laden with extremophiles into interstellar space, turning these icy bodies into accidental arc ships. The search is already yielding surprises. Lab experiments exposing Earth microbes to simulated cryovolcanic conditions, extreme cold, ammonia-rich brines, and vacuum pressures show some organisms not only survive but metabolize, however slowly. Tardigrades, those microscopic extremophiles famous for enduring space's vacuum, revive after years frozen in artificial methane slush. While no one claims this proves life exists on dwarf planets, it demolishes the assumption that such environments are inherently sterile. What makes this quest electrifying isn't just the science, it's the philosophical shift. Cryovolcanoes force us to abandon Earth-centric definitions of habitability. Life here needs liquid water, but on Pluto, it might thrive in nitrogen ice fractures. Energy on Earth flows from sunlight or geochemistry, but on Ceres, it could come from radioactive decay interacting with salt deposits. Each eruption sampled, each plume analyzed, brings us closer to answering whether life is a cosmic fluke or an inevitability waiting in the frozen dark. From Pluto's towering ice mountains to Ceres' solitary peak, cryovolcanoes have shattered our assumptions about where geologic life can thrive. These erupting ice giants aren't just oddities, they're cosmic trailblazers, rewriting the rules of planetary activity and proving that even the coldest, darkest corners of our solar system pulse with hidden energy. Every plume of nitrogen gas on Triton, every salty ooze from Ceres' Ahuna Mons, and every slushy eruption on Pluto's Wright Mons is a reminder that the universe thrives on surprise. These aren't dead worlds frozen in time. They're dynamic landscapes where chemistry and physics conspire to create eruptions unlike anything on Earth. What makes these discoveries so thrilling isn't just the geology, it's the possibilities they unlock. Hidden oceans, warmed by tidal forces or radioactive decay, could slosh beneath the ice of dwarf planets, offering refuge for life in places sunlight never touches. The same antifreeze chemicals that keep Crivell, Conos erupting might also sustain microbial communities, turning these frozen worlds into unexpected havens for biology. And let's not forget the sheer resilience of these systems, how a tiny body like Ceres, barely 900 kilometers wide, can stay geologically active billions of years after its formation. If that doesn't force us to rethink what lifeless means, nothing will. The real magic lies in what we haven't found yet. With every mission, from New Horizons' Pluto flyby to Europa Clipper's upcoming journey, we peel back another layer of the mystery. Maybe the next spacecraft will catch a cryovolcano mid-eruption, its plume sparkling against the void. Or perhaps a lander will drill into icy flows and stumble upon chemical traces that hint at something even more extraordinary. The search isn't just about understanding these alien landscapes. It's about confronting the profound question of whether life, in some form, could exist in the universe's most unforgiving places. So as we gaze at these distant, icy worlds, let's not see them as static relics of the solar system's past. They're alive, not in the way Earth is, but in a language of slush and gas, of hidden heat and slow-motion eruptions. Every discovery brings us closer to decoding that language, to understanding how these frozen giants shape their own destinies. And who knows, the next great revelation might come from a plume spotted by a telescope, a crack in the ice glimpsed by a probe, or a strange reading in a spectrometer that makes scientists pause and say, wait, that shouldn't be possible. The universe loves a good plot twist, and cryovolcanoes are some of its best stories.